Today we're going to do a chapter two. It's a little bit longer than chapter one. It's going to cover science, matter, energy, and systems. A couple of things I'm going to emphasize is that we're going to look at matter, and we're going to look at like law of conservation of matter, law of conservation of energy, and the big theme is we're going to go from what they say high quality matter to low quality matter. Remember, matter and energy cannot be created or destroyed. We're going to look at how we go from high quality energy to low quality energy. And we're going to look at how science plays a role in that. And then the second part, we'll look at different types of ecosystems, how things are recycled. We'll look at what they call trophic structure, who eats who, basically, in those types of systems. But one thing I do want to mention, when you're looking at this, especially in terms of matter and energy, maybe the first part of this chapter, you're going to see how things go from high quality to low quality, and how low quality, even though it's there, is not nearly as useful. So a couple of things. Let's talk about matter. Let's go ahead and talk about matter. Matter is basically the stuff around us. That's just the quick definition. It's just the stuff. It's the air, it's the land, it's the water. It's just the stuff around us. A couple of things. Law of conservation of matter can be created or destroyed. So the amount of matter we have, we can go from one form to the next. Or we can go from like solid to liquid to gas, vapor, whatever the case may be. But the amount of matter, the total amount of matter around us can never be created or destroyed. So the mass of it has to stay the same. However, we can change it. Again, I want to mention that there's physical change. This is, for instance, like melting gold. If you go to these places now that buy gold, they'll get like a gold ring, 18 karat gold ring. They'll melt it down. And normally, when I say 18 karat, you'll have gold, silver, and copper in there. They'll melt it, so it's still gold, still silver, still copper, but just in a different physical state. It went from a solid state to a liquid state. That's a physical change. Or like say that you grind up aspirin. It's still aspirin, but just in a different change. Cutting up aluminum foil, still aluminum, but just in a different form. Chemical change, this is where you form something new. Basically, you're rearranging chemical bonds. Like, say you have gasoline. Again, you're not destroying it. You're not destroying matter. You're just changing the form of it. So you have gasoline in your car. So you pump in gasoline to your gas tank. When you ignite your car now, it's going to burn. And actually, what you form is carbon dioxide gas and water. That's what you form. You give off energy too. We'll talk about that. So gasoline is in it's formed something new. You form carbon dioxide gas and water. It's a new compound. Basically, you've just arranged the chemical bonds. Physical change, you don't arrange the chemical bonds. You just change the physical state. Like you melt something, you freeze something. But chemical change, you're forming something new. I mean, that's not gasoline anymore. You've burnt it. So that's that combustion reaction. So there's physical and chemical change. Um, take a look at the basic structure of an atom. Again, we're probably familiar with this. There's going to be electrons. There's going to be protons. And again, I use our symbol. And then there's neutrons. So protons and neutrons are in the center. That's the nucleus. And then the electrons are surrounded. So again, the electrons, they're circling around the nucleus. And again, this is a simple diagram for it. This is called like the Bohr diagram. Atoms really don't look like this. It's much more complicated than this, but this is a good way of thinking of it. And again, I think of it like this in most cases, and I teach chemistry because you can understand a lot of chemistry just by looking at it. Each element, so element are the basic building blocks of everything around us. We'll look at that in a second. Has a unique number of protons. So they all have unique numbers. So hydrogen has a unique number of protons. Carbon has a unique number of protons. Like carbon has 6 protons, hydrogen has 1 proton. Something like gold has like 79 protons. Something like sodium. So you always talk about watch your intake of sodium. That has like 11 protons. So I'll put P positive is protons. So each element now has its own unique number of protons. It's in the center, so it's going to be in a nucleus, like this is a nucleus there. So protons and neutrons reside in the nucleus, and the electrons are surrounded. Hydrogen doesn't have a neutron. That's why you don't see it there. It just has a proton. But every other element will have protons and neutrons. So elements, so let's talk about a little bit about this. So we talk about atoms. So atoms are the basic building blocks of matter. Atomic number is the number of protons. So that's the one in the nucleus. Mass number is the number of protons and neutrons. So to say that I have carbon. We'll spend a lot of time talking about carbon. And say that carbon's mass number is 12. So that means now it has 6 protons plus 6 neutrons. The protons you can get from the periodic table. Neutrons you can't. So that's what that means. That's the mass number, number of protons and neutrons. Electrons have such a small mass, so the mass of an atom really just depends on the number of protons and neutrons. So again, atoms are the ones that are the basic building blocks of elements. And again, we look at mass number, atomic number, that's number of protons, and then mass number is number of protons and neutrons. Couple of things. When you look at the periodic table, so say I was mentioning carbon here. That's 6. That's the atomic number. So that's the protons. That top number is the atomic number. This bottom number, it's in the decimal form. That's actually called the atomic mass. It's related to the mass number, but not exactly. We're not going to spend a lot of time on this, but that's called the atomic mass. We'll get into more details later. So this is gold. So gold actually has the symbol AU. So some of these are named after their Latin name. So AU is actually gold. Its Latin name is actually aurum. So sometimes when you see these different names, it's named after the Latin form, like sodium, nerium, I think. This bottom number is the atomic mass. This top number is the atomic number. And again, we mentioned this also. Atomic number, there's carbon, that's a symbol, and then this is the atomic mass, atomic weight, atomic mass. This is related to the mass number, but it's not exactly with the mass number. And we may talk a little bit about that. So we talked about atomic number, mass number. So these are isotopes. Same element having different, it should say a mass number, but same number having different mass numbers. So same atomic number, different mass numbers. Like for instance, carbon has 3 isotopes. It has 3 isotopes. So the number of isotopes, the number of protons stays the same, but the number of neutrons is different. So basically, number of neutrons, I'm going to put NO for neutrons. That's neutrons are different. In class, we'll go over this if we need to. I'm not exactly sure how much we need to know, but we'll talk a little bit about it. So isotopes, different number of neutrons. Basically, same element, different number of neutrons. So they have a different mass number associated with it. And I think let's just take a look at this. It's okay. So you can say carbon 12. So this right here, this 12, 13, and 14, this refers to the mass number. So if I go analyze carbon, say I go into the jewelry store, so diamond is pure carbon. That's pure carbon. If I go analyze it, I'll find out I'll have carbon 12 atoms. These are the atoms there. Most of it's carbon 12 atoms. It's about 98.1%. I'll have a little bit of carbon-13 atoms, maybe 1.1%, and then just a fraction of carbon-14 atoms, maybe 0.1%. So if I look at something as pure carbon, and graphite's pure carbon too, by the way. If I look at diamonds, you go to a jewelry store, if I analyze the atoms that make up diamond, that make up that carbon, most of it's carbon-12, so 6 protons, 6 neutrons. The number of electrons stays the same too, but the number of neutrons are going to vary. Carbon-13, 6 protons, 7 neutrons, 6 electrons. Carbon-14, 6 protons, 8 neutrons, 6 electrons. So say I had carbon-14, that's the mass number. Well, if I have 6 protons, and I'm going to look at number of neutrons, well, it has to be 8. Because 14 minus 6 is 8. So again, most elements have isotopes. Same element, same number of protons, different number of neutrons associated with it. Molecule, 2 or more atoms held together. So for instance, now I talked about carbon dioxide. So that's that big greenhouse gas, global warming, CO2. If you did have any carbon dioxide gas in the atmosphere, by the way, it'd be too cold for us to live. So you do need some. So you always need some carbon dioxide. I think with all these emissions, we've just increased it a little bit too much. But basically, you do need some in there. And this stuff absorbs ultraviolet light or infrared light. So this stuff will absorb infrared light. We'll talk a little bit about that in class if we need to. Ions are charged particles. Charged ions, they have a charge associated with it. So molecules, and these are neutral, which means number of protons equals number of electrons. In this case, number of protons does not equal number of electrons. So basically, electrons are going to be lost or gained along the way. We're not going to spend a lot of time on there, but just notice ions are charged species, like something like sodium. We'll have a positive 1 charge. Chlorine will have a negative 1 charge. When they combine now, you'll have table salt. And again, what happens is an electron gets lost. We're not going to go into all the details. And so now you have 11 protons and 10 electrons rather than 11 protons and 11 electrons. Metals will lose. So sodium is a metal. So metals will lose electrons. Something like chlorine will gain. So sometimes they can lose or gain depending on the type of compound, type of element they are. You probably heard of pH. It tells you how acidic or basic a solution is. It actually measures the concentration of H plus ions. Again, ions are charged particles. The higher the concentration, the more H plus, the more, I say this, the more acidic something is, but lower the pH. So it's kind of like the opposite. And the reason is because pH is a log. It's a logarithm. But basically, lower the pH, the more acidic something is. And the reason is that when I have water, water will break down into a tiny bit. Most of it's still going to be water. There's a fraction of hydroxide ions and H plus ions. So water is basically H. When I write HOH, it's actually something like this. It's hydrogen and some hydroxides. When it's neutral, these concentrations are the same. And this is hydroxide. OH is hydroxide. And we'll go over it in class if you need it. I'll have to take a look and see if you need some of this. So if it's neutral, pH is 7. Hydrogen and hydroxide ions are the same. And again, if it's acidic, so in fact, I think let's go into the next. Let's go. If it's acidic now, H plus, so when I put the brackets, it means concentration, is greater than hydroxide concentration. So there's always a competition. Hydrogen ions and hydroxide ions. If it's a base, there's less hydrogen ions than hydroxide ions. So that makes it basic. The scale goes from 0 to 14. 0 is most acidic. So again, the lower the pH, most acidic. 14, you can say it's the least acidic or most basic. Basically, if it's acidic, so if it's an acid, it goes from 0 to less than 7. If it's a base, so something like sodium hydroxide is a base, it's greater than 7 to 14. So 0 to 7, so 7 is neutral, and then so anything less than 7 is acidic, anything greater than 7 is going to be basic. And again, these are some substances. Notice one thing about it. Most like drinks and foods are going to be acidic. So like coffee, tomatoes, vinegar, stomach acid, lemon juice. These are acidic. Acids have a nice sour taste, which we like. Basic stuff are like soaps. So soaps are bases, and we don't like stuff that tastes soapy. At least most of us don't. So most foods are actually going to be acidic. Uh, Blood is a little bit above 7. Seawater is a little bit above 7 because it has some salts dissolved in there. So baking soda is a base. Milk and magnesia, these are antacids. So you take those to neutralize the acids in your stomach. These bases can be tough. Bleach, oven cleaner, sodium hydroxide. These can be some nasty bases. Sodium hydroxide is used to make soaps, etc. This stuff has kind of, like I said, it has kind of a bitter taste, which we don't like. Bases do. Bases are bitter, which we don't like. And then they have a soapy taste because they used to make soaps. Acid foods taste better. Most foods are going to be acid. It has a nice sour taste, pickles, etc. All drinks are going to be acidic. You can buy now, when they say basic, they also call it alkaline. So nowadays you can buy alkaline water. It's supposed to neutralize the acids in your body. Again, that's a base. So I want to continue a little bit. This time I want to talk about organic compounds. So organic is, when you study organic chemistry, it's the chemistry of life. And the reason is because organic compounds contain carbon. And most life processes contain carbon. We're going to break it down into 4 very basic groups. There's proteins, carbohydrates. So carbohydrates are sugars, something like glucose and fructose. Proteins are like long chain amino acids. Lipids are fats and oils, or oils. The only difference is fats are solids at room temperature, oils are liquids. And then nucleic acids, DNA and RNA. So these are 4 basic groups of organic compounds. Foods will have proteins, carbohydrates, and fats. So you look at the label of a food, it'll tell you how many proteins there are, how many carbohydrates, and how many lipids. They all contain a certain amount of calories, which is basically how much energy each type of these molecules have. Nucleic acid, again, these are for DNA, RNA, these are chromosomes, etc. A few things about this one. Uh, Proteins, again, some carbohydrates, not all of them. Something like glucose and fructose are not macromolecules, but some proteins, nucleic acids, these are macromolecules. These are just very large molecules. Uh, Plastics are actually macromolecules. So if you buy like something like polyethylene, that's just a combination of small ethylene molecules bonded together. So macromolecules, they're just polymers basically. Uh, and again, monomers are a single unit and they link up together to form a large molecule. It's called polymerization. So it's kind of like you have small Legos, individual, they're the monomers. When they're combined, they're the polymers. So same thing with macromolecules, very small individual units, one of them, and then they linked up, they're going to form macromolecules, or you can call them polymers. Like for instance now, like glucose. So glucose is actually a monomer, but something like starch is a polymer. So glucose is a monomer, starch is a polymer. It's just a bunch of glucose units linked up together. Simple as that. Monomers are one, polymers are more than one. Again, I like to think of like starch. So potatoes have high starch content. There's a bunch of glucose linked together to form that polymer, which is just a polymer of glucose. DNA, again, we all know about DNA. You may have like 500 million of these nucleotides. They're the ones that make up DNA. Maybe 500 million of these linked together. Um, these are what they call the bases that make up DNA. So there's only 4 types of DNA. They all have a different base, either A, T, G, or C. A couple of things: the G and C linked up together to form that kind of double helix, and then the A and T bases linked up together. We don't have to go into the details, but they linked up by something called hydrogen bonding. Again, DNA stores genetic information. And again, this is what I was talking about. The A and T's of the DNA hook up, G and C hook up, etc. Again, this is genetic information. This is what I was talking about in terms of matter. There's high quality matter and low quality matter. High quality matter, this is stuff that's highly concentrated, it means there's a lot of it, and concentrated means all in one spot. Near Earth's surface and high potential. So this is stuff like fossil fuels. That's a good coal. Coal is an easy way to access it. It's just right there, easy to mine. That's a high quality matter. Low quality matter, not very concentrated. It means it's kind of spread out in very low amounts. I always keep mentioning the rare earth metals. So the rare earth metals are used to make batteries, and they're used in computers and cell phones. They're not really rare per se, but they're very diluted. I mean, you have to get a lot of ground to get a lot of it. So it's there, but it's all spread out. Gold nowadays is low quality. So gold, you used to get big chunks of it, but now it's just gold dust basically. You don't have big chunks much anymore. So it's just kind of diluted out and hard to get to, very expensive to get to a lot of these minerals nowadays. Something like aluminum and iron and copper are not that difficult, but other stuff is. So low quality, not concentrated, very deep underground or widely dispersed. And the main thing is it's low potential. Same thing with high quality is the opposite. It's high potential, easy to get there. It's just right there. I mean, oil is just right there. Basically, you pump it into the ground. It's just right there. Same thing with coal. Coal is just right there. Energy, capacity to do work. And energy is like matter. It can't be created or destroyed, but you can change it from one form to another. So there's law of conservation of matter. Matter can be created or destroyed. The same thing with energy. Energy cannot be created or destroyed, but you can move it from one form to the other, just like matter. There's basically kinetic energy, which is energy of motion. So what heat is really things going from high temperature to low temperature. It's transfer of heat or transfer of energy from high to low temperature. So heat flows from high to low. It's really how fast the molecules are moving. It's really how fast molecules are moving. The faster they move, the higher, the more heat there is, the higher temperature, basically. Light is a form of energy. Again, this is just like electricity, moving car. These are forms of kinetic energy. These molecules are constantly moving around. Stored energy, always think about as food. Food has potential or stored energy. Then once you eat it, it breaks down to glucose or whatever the compounds it is, and so you produce breaks down to kinetic energy afterwards. But food is good stored energy. They always talk about a kid on top of a slide. Chemical energy, so like gasoline, before I burn it, it has a lot of potential energy. Once I start burning it, then it's kinetic energy. So one is motion, something constantly moving. The other one is just going to be stored energy. This is different types of light that come from the sun. Visible light is the only one we can see with they call it naked eye. Others you can detect. There's infrared, microwaves, TV waves. The ones towards the left right here, ultraviolet, X-rays, gamma rays, these are dangerous. This is stuff that can mess up with your DNA because they can knock off electrons off your DNA, which means mutate. So they can mutate your DNA, and so if you mutate it enough, so basically they mutate DNA, increase your risk of cancer, etc. Other stuff like infrared, microwaves, TV waves, these are very safe. And remember, if you go do tanning, you always got to worry about that ultraviolet radiation. This is why you're not supposed to tan more than a certain amount per week, etc. Let's take a look at something about energy. It's governed by two different laws. First law of thermodynamics. Again, this is the law of conservation of energy, can be created or destroyed. And then also entropy. Uh, when energy is changed from one to the other, it becomes more disordered, which means it becomes less useful. Like, for instance, food, right? Food is very high potential, very useful. But once you eat it, breaks down into your body, it's used to run your process in your body. A lot of that energy becomes heat. And heat is basically, really, it's not very useful in most cases. So it becomes heat in your body. So it's not very useful. Food was very useful. But once you eat it and it starts breaking down, it's not very useful uh, anymore. Same thing like when you have gasoline. Well, gasoline has a lot of potential, right? A lot of potential energy. When you burn it in your car, it transforms into like, you go from potential to like, um, I guess it's called not physical energy, mechanical energy and stuff like that. But also a lot of energy ends up as heat. And so that heat makes your car hot. If your car is very efficient, your engine won't get hot, but it does because a lot of the energy becomes heat. It's not as efficient, so it becomes heat. So heat is not very useful for the most part. So you'll see that even though the amount of energy in the universe stays the same, a lot of it becomes heat, and heat is not that useful. So again, food is more useful, gasoline is more useful. Once you burn it, it becomes heat, and it's not quite as useful. So the amount of energy stays the same, but it goes from high quality energy to lower quality energy. And again, we've talked about this again. High quality energy, nuclear energy, solar, fossil fuels. Low quality energy often ends up as heat. Now, let's take a look at organisms. And though this may seem kind of obvious sometimes, we should talk about what makes organisms alive and some not, because you think of it, well, plants and animals are alive, rocks are not. Some of these things, like if you look at a virus, it may be difficult to determine, is a virus really uh, alive? So we'll look at some definitions that biologists uh, look into when they consider something being alive or not. So for something to have the properties of life, it must have all these characteristics. Let's go through them. Must be able to reproduce. Uh, they have to grow and develop. So, babies turn into adults. Even plants, they go from small to large. Plants can reproduce too. Plants reproduce too. Energy use, like plants, they use photosynthesis. They take energy in from the sun, carbon dioxide, make into food, etc. We do the same thing. We eat food, we convert that to energy to make our bodies run efficiently. Uh, Order, so you can have very complex order, like in humans and animals, or something much simpler, like some of these single cell organisms, etc. Again, we talked about they all have to have cells. So plants and animals, they gotta have cells. Some of these, like us, have trillions of cells. Some can have just one cell. So, but again, they gotta have cells to fit into these types of conditions. And the definition of a cell, simplest structure possesses all the properties of life. Gotta have response to the environment. Um, and again, what I mean by this is something like homeostasis. Like we got to have a certain pH in our body. It's around 7.4. So whenever we take something in, we eat food and stuff, our body will adjust. So we maintain a certain pH, a certain electrolyte level. That's homeostasis. So something's alive, it will adjust. We'll respond to the environment to maintain our internal conditions. That's always important. So you have to maintain homeostasis to live. And so stuff that's alive, organisms that are alive, plants or animals, will maintain homeostasis. We'll keep our internal environment within its very narrow limits. Again, pH. The pH has to be around 7.35 to 7.45. Otherwise, we'll die. So our body maintains that pH. We got to evolve. So even though something like a virus evolves, a virus is not considered a living organism. We'll talk about why not. But evolution, that's the process of things that are alive. They'll change their gene pool from one generation to the next. So they have to adapt to the change in Earth. So organisms, living organisms adapt basically to a change in Earth. We talk about viruses. Uh, it's not considered alive. So even though they display some of these properties, like they evolve, like you see this now, right, with the new strain of COVID-19 virus, so it evolves, right? But it's not considered alive. They get their energy from by infecting uh, other cells. Viruses do. Viruses can't reproduce on their own, so they have to infect another cell and use their cell's DNA materials to to reproduce. When they say a virus is infectious or not infectious, it doesn't mean that it's alive or not. So biologists consider viruses not living organisms. They get their energy. They don't have their own energy. They can't reproduce their cells. They have to infect a cell. They're not comprised of cells, but they do evolve. So they have some characteristics, but not.
So let's kind of shift gears a little bit. Let's talk about ecology. And ecology is just simply how living things react with each other and the environment. So it's not just how humans and animals react to each other, but how they react with plants, minerals, land, air, etc. One thing, again, just to make sure, is that it's not the same as environmentalism. So again, environmentalism is that political, social, political movement. Ecology is a hard science, just like chemistry, physics, engineering, etc. So there's different levels of ecosystems. So let's take a look at this. So the first one, you have oxygen, you have molecules, you have cells. And again, it gets more complicated as you go up. So as you go up, it becomes more and more complicated, more and more interactions. We have organisms. So we talked about organisms, what makes something alive. And then population. So population is a group of individuals living in the same place, like a bunch of deer occupying some certain area of Tennessee. That's a population. And then community be different species. So for instance, now this is like the predator and prey. Say you have wolves in the area. How the wolves interact with the deer, etc. So that's a community, different species interacting with each other. So population, same individuals, same group of individuals, deer, maybe people, right? Uh, mention wolves. You go to community. How predator and prey, I like to think of it, is how different species react with each other. And then ecosystems, it's how the community reacts with non-living things. And again, these things can be how they react with the soil in the area, the water in the area, minerals, etc. That's ecosystem. And then finally, biosphere. Biosphere is just any part of the earth, the whole planet really, in which life is found. A couple also things, it's also a couple of good definitions. When they say biotic, you're talking about living components. So biotic are things that are living. Abiotic are non-living things. So abiotic would be stuff like water and soil. So again, we make these distinction. Again, when they say ecosystem, it's composed of both biotic and abiotic. It's not just living things. It's water, soil, air, etc. Couple also things. Ecosystems have four major components. There's the atmosphere. That's just the gases surrounding us. Hydrosphere. So whenever you hear hydro, you're talking about water. That's water on or near the Earth's surface. So these are things like lakes, oceans. Also, if you're drilling for water, so that's easily accessible water. So those are the hydrosphere. Geosphere, solid interior of the Earth. So again, when you drill down into the Earth, those layers, the crust and all that, those are the geospheres. And again, I mentioned biospheres, is just any part. You're talking about water, air, land in which life is found. So we're just take a look what we're talking about. So again, the atmosphere, this is up in the upper layer. This is where life exists. Soil, there's rock. And again, if you drill down far enough, you get into the hot, molten core of the Earth. So again, hydrosphere is the water, atmosphere is the air, geosphere, crust, mantle, core of that. Again, biosphere is just any area in which you have living organisms, plants and animals, etc. So a couple of things, and this is important. There's three main factors that sustain life on Earth, and I mentioned before, the sun. So when the sun eventually burns out, like billions of years from now, there probably won't be any more life on Earth. And so energy flows from the sun. So sun is the main source of energy. And what we'll show also is that, so we always go from a high source of energy. Again, high source means high capital of energy to a lower source. And a lower source is less useful. So we don't lose energy by law of conservation of energy, but energy goes from a higher, more usable source to a lower, less usable source. Again, always kind of keep that in mind. Same thing with matter. It goes from a higher quality matter to lower quality matter. You need nutrients in the cycle, in the biosphere. Again, these are minerals, nutrients to help things grow. Without those, things are not going to grow. And then you can say that gravity kind of holds things together. When I say nutrients, again, this is everything from biotic to abiotic. Those are abiotic and biotic sources. Again, things are recycling with each other too. We'll look at the next slide at how things recycle, how things flow from one energy system to the next. We'll look at this. Again, we've kind of talked about energy flowing through ecosystems. So the sun is the primary one. Enters the system as sunlight. Again, there's different types of light. The ones we're familiar with are visible light, but there's other types like ultraviolet, infrared, etc. That solar energy, this is by photosynthesis, is produced now by plants, right? It takes that carbon dioxide gas and that energy from the sun, converts it into food, basically, into sugars and oxygen. And so the plants use some of that to grow. The plants now are going to be eaten by something like cows. And again, each time the amount of energy is decreasing. So again, it's transferred or lost to something like heat, basically. So it's less useful energy. It's consumed. So that food, right, those plants are consumed by the cow. So that food has high potential energy or high energy. Once it gets into the body, it breaks down. It breaks down into sugars and stuff. And a lot of the energy is lost as heat. And so that energy becomes less quality energy. And again, now a lot of that heat gets lost from the body too. So the body's not a perfect insulator. And then also you expel a lot of carbon dioxide gas too. So again, carbon dioxide gas gets expelled back into the atmosphere. So again, it's a cyclic structure. You go from the sun, plants convert that sun by photosynthesis into food and into energy that plants use to grow. Energy is eaten by the cows. Cows use that food now, breaks it down in their body, have that body maintain the systems, and then some of that energy is expelled as heat. But again, you go from high quality to low quality energy as you progress through these systems. And again, we talked about carbon dioxide gas, same thing. Carbon dioxide gas from the atmosphere gets converted to food, right, to sugars by photosynthesis. So again, carbon dioxide is going through there. Sugars are eaten by the cows. And again, these are from the plants, right? So sugars. And then what happens is they release carbon dioxide gas when you breathe. So again, it's another cyclic type structure. A few things also. Let's talk about trophic structures. And this refers to the place of the organism in the ecosystem. And this is really prey versus predator, or who eats who, really. That's how this system really works. Who eats who. So we have a trophic structure, basically who eats who. A few things, autotrophs, these are ones that synthesize their own food. These are going to be plants. we've talked about photosynthesis a lot. These are plants. So plants take carbon dioxide gas from the air, convert it to food, etc. Heterotrophs, these are going to be animals. So they have to attain their energy from basically eating other organisms. Again, and these things include plants too. So it's not just like a lion eating a zebra. It's like humans eating plants, cows eating plants, etc. So again, we can't synthesize food ourselves. Animals can't. So we have to get it from other sources. So autotrophs are plants. Heterotrophs are basically going to be animals. And again, that's part of the trophic structure. You have autotrophs, and these are producers. And then we're the consumers. These are the heterotrophs. And again, there's different levels of them too. There's some that just eat other producers. Those are herbivores. And again, that's going to be, those are the ones that eat plants basically. So herbivores eat plants. Then omnivores are ones that are like us. We can eat plants and other animals, and plants and meat. Then secondary eat the primary, tertiary meat the secondary, etc. So herbivores are the first level. They just eat plants. They get their energy solely from plants. And what you'll see is that's the best way from the environment in terms of being the most efficient is the ones that eat plants. That's where you'll lose, or you keep the more quality energy. But as you go up from primary to secondary, tertiary, you start losing a lot of energy along the way. And we'll look at that as we go. We've heard a lot of this. There's detritus feeders. These are like, we always talk about vultures, insects, some earthworms. They'll eat these dead organisms. So you see them dead on the side of the road. You always see vultures, but there's maggots there, earthworms, etc. And then these decomposers, these are bacteria and fungi that once they attack these dead organisms, they'll release these nutrients back into the soil. So these are very important. Though we always think bacteria is being bad. A lot of bacteria and fungi are good, and they are necessary for us. So let's take a look at this. So the first trophic levels, these are the producers. These are the plants. And then, again, we kind of go up like this. Again, we lose energy as we go across. Second trophic level, these are the primary consumers. These are ones that just eat plants. So plants are the producers. These are ones that just eat plants. Secondary, the third trophic level, these are the carnivores. So these are ones that eat the animals that eat plants, etc. And then tertiary, the ones that eat the secondary consumers. For the most part, you don't get much higher than tertiary consumers. So in this case, you have solar energy, you have the plants. Plants are eaten by these worms. These worms are eaten by the birds, and maybe the birds are eaten by an eagle or something like that, or a snake. I mean, so you have all these different levels, etc. It's just kind of like you have grass. The zebras eat the grass. The lions eat the zebra. So the grass is going to be the primary. The zebras will be the secondary, and then the lions will be the tertiary. Again, the third level, again, those are hard. You can't get much higher than, not too many things are going to eat a lion. So a lot of times after that third trophic level, it's third or fourth, you don't get much higher than that. Couple things, I mentioned this, the usable energy decreases with each level in the food chain, and only about 10 to 20% is passed from each level. Again, we'll look at why that's happening, and we call this ecological efficiency. So the most efficiency are actually the plants, right? They're the most efficient. These are going to be the primary ones. Those are the most efficient. And then the second one are going to be ones that just eat plants. So the ones that just like, vegetarians, right? Those are the ones that are the second most energy efficient or ecological efficiency. And then it gets worse or less and less as you go up each chain, because you only a small fraction, 10 to 20%, actually pass from one level to the next. Let's take a look at how this works. So say you have a worm, and again, that caterpillar, I shouldn't say a worm, a caterpillar, it eats the plants, right? And so it's that, these plants have different amount of energy, so it consumes 100 kilocalories of energy. One thing, when I talk about food calories are actually kilocalories. So when I say food calories, you're actually talking about kilocalories. But say that this caterpillar consumes 100 kilocalories of energy, so 100 calories. Well, it'll lose like half of that to like, feces. It'll use about 15 for growth. So right away, you've lost about 65% of your calories that you consumed. And then about 35 is used for cellular respiration. So really, this is the only thing that's available for it. It uses it for growth, right? So it gets a little bit bigger. And so you only gain about 15%. You've only really 15% of it is only really usable, because that's the one that makes these caterpillars bigger and get these caterpillars get eaten by worms, by birds, etc. So the respiration you lose from breathing, you lose it through feces. Only about 15% of it, or you say 15 kilocalories, are going to be used for growth. So that's what they call a biomass. So it grows a little bit because of that. And so you have the sunlight. And again, if you look at it, we're not terribly efficient in going from sunlight to converting it from plants converting it into sugars and food. So it's only about 10% efficient. So you have a million kilocalories, you go down to 10,000 calories. Plants get eaten by maybe a cricket or grasshopper. Only about 1,000 calories is going to be passed on to that mouse or rodents. So now I'm down to 100 kilocalories, and then eventually those snakes will eat the rodents. Only about 10 kilocalories of energy is being passed down initially. So you go from a million up to about 10. So you lose about 10% or lose about 90% each time. You only pass on about 10% of that energy. So you go from a million to 10,000 to 1,000 to 100 to 10. And this is why normally after tertiary consumers, you don't see it much higher than that, because there's not enough energy is left. And this is why snakes have to move around a lot. They're not getting enough energy, food sources in a particular area. So plants can stay secondary, so can crickets, rodents move around a little bit more, and then finally these snakes will move around a lot because they just don't get enough energy to begin with.
So let's kind of continue. Let's take a look at some of these ecosystems. And a couple important concepts is, let's take a look at gross primary productivity. So we talked about this, how plants convert sunlight into sugars, glucose, energy, etc. So that's called gross primary productivity. In different areas, so you're going to talk about ecosystems, like they always talk about save the wetlands. So I was in Louisiana, close to New Orleans, save the wetlands, because the wetlands produce a lot of energy that people use. All these different consumers will use. Net primary productivity, which is probably the most important. So there's gross, is how much energy they produce. Net primary is what's left over after these producers keep themselves alive. So again, plants, animals have to keep themselves alive, mostly through cellular respiration. Well, how much is left over? That's like net primary productivity. It's like they have gross domestic product for government is how much money a country produces per year, and then the net is how much is left, which is probably the most important part after that government spends all the money on its necessary things, etc. And so a couple of things to be let's take a look at this. So again, I mentioned this before, like stuff like swamps and marshes, they give off a lot of energy with that. Deserts, they're not very useful. We see that, right? There's no plants, very few animals live in there with this. Aquatic systems, again, estuaries, those are the areas that kind of where salt water and fresh water meet. Those have a lot of gross primary productivity. Lakes and streams, an open ocean, not quite as much. So again, this is why they always say to have sustainability, because they give off all this energy. They want to save swamps, tropical forests. Again, if you're in like Amazon, so you're in Brazil, Africa, they have all these big tropical forests. Even stuff like in Indonesia and areas like that. And then notice that it progressively decreases. So you get down to like, again, deserts are basically nothing. And then for aquatic systems, estuaries, lakes and streams, continental shelf, etc. So let's take a look at the water cycle, how water gets cycled throughout the earth. A few things is it comes from, well, we know precipitation, so we get rainwater, evaporation, so these are from evaporation from like oceans and lakes. So again, water will evaporate, just like water any place else will evaporate. Glaciers, right? They'll evaporate off glaciers too. But also one of the most important one is transpiration. People kind of underestimate this. Evaporation from leaves of plants. And this is a lot, by the way. I think sometimes we don't realize how much comes from transpiration, how much of the water comes from that. This is why we always talk about, if wetlands, forests, deforestation, and stuff like that, we start having less plants now, we'll have a lot less water. And that's a very important concept. So again, uh, also with less plants now, you have a lower renewal of water. So again, we need this kind of a cyclic system. So again, precipitation, which we were familiar with, evaporation from oceans and lakes. Again, don't underestimate how much water we get into the atmosphere by transpiration. Again, when this water gets in the atmosphere, it fills up the clouds, and the water will come back down towards us. So again, you have areas that have been deforested, so deforestation. All of a sudden, the amount of rainfall goes way down. And again, it's because of this transpiration that we need. So again, let's take a look at this. And these are kind of a good graph for that. So we have a lot of groundwater. So this is water that kind of seeps down into the ground. So we have wells and stuff to get it. We get a lot of water from surface runoff. And what happens also, if you have less plants and trees now, they're not going to absorb a lot of this water. And this water is just going to go away uselessly, basically, cause flooding and stuff like that. So again, we need trees and plants to kind of contain some of this water. They absorb that water, it goes into the ground, and we'll have more groundwater, etc. Rather than this runoff in which this water just kind of goes away and is not going to be useful. Again, this is why if you have deforestation now, you have a lot of droughts and floods, etc. Again, talk about water gets evaporated, condensation. This is going from liquid, gaseous water to liquid. So when you wake up in the morning, you always see condensation on your windshield. That's just the hotter water molecules in the air hitting the windshield, and then it kind of condenses down. So again, we have this water cycle. And again, you don't want to mess with it. You don't want to mess with this cycle that you have. And again, if humans, again, we need trees and stuff. We got to make paper and stuff like that. We understand that. We need it for lumber. But you have to be careful. You have to kind of plant these up. Otherwise, the earth can't recover the way it should. And again, we talked about human activities. And again, a lot of this is just part of society. And so to have sustainability, again, we have to use our resources, we have to use our engineering, we have to use education, and we can do it. I'm always a real positive person on how to replace these. Again, clearing vegetation, draining wetlands. So a lot of times, again, I always kind of mention Louisiana, they have a lot of wetlands down there. These wetlands get drained, and what happens is you have areas now that are just concrete, like you have cities or kind of like desert areas. They're not going to be able to absorb water as much, and that's going to cause an increase in flooding. You see this a lot around the coastal cities. They drain wetlands to build, apartments, cities, etc. It's kind of a concrete environment. You can absorb a lot of that water that comes off from runoff, rain, etc., and then you have this increase in flooding. And we kind of talked about it. for some of these processes. Again, condensation, remember us is going from gas to liquid, so that increases the amount of water in our system. Evaporation now, so a lot of the surface water evaporates. It's always mostly from the surface. And again, these are a lot of pathways that we get water from. You get it from the ocean, groundwater, lakes, and reservoirs. And again, we've talked about that. Runoff, by cutting down, let me get a better pen for this. Runoff from cutting down trees and stuff like that. And so this is why in terms of sustainability, you don't want to change the ecosystem too much because they all kind of work. I always call it a symbiotic relationship. Let's take a look at the carbon cycle. A few things about this is that the carbon cycle, again, carbon cycle comes from living organisms, but also it can be from abiotic. And we've kind of talked about this a lot, from carbon dioxide from the atmosphere, in which plants can transfer it into sugars and food. So again, if one thing from this chapter, always talk about photosynthesis, the importance of it, the importance of plants and trees to convert this carbon dioxide gas into food, so the plants can grow. And then once these plants are growing, people can eat plants, animals can eat plants, and it goes from there. So again, the carbon cycle now, remember, it's both biotic from living things, because most of our body has a lot of carbon in there, and then also abiotic relationship. A lot of that carbon dioxide gas, we get it from respiration, because when we breathe out, we're returning carbon dioxide gas to the atmosphere. We also get it from burning fossil fuels, etc. And so we got to be careful with this. If we have too much carbon dioxide gas in the atmosphere, you can form something called carbonic acid, which you do form it, but if you have too much, and this can acidify lakes, oceans, etc. So if it's too acidic, a lot of plants and fish and stuff will die, because this acid rain, so this is acid rain. This acid rain, what happens is it can destroy the wax off leaves, and then they'll destroy the plants because they have that waxy leaves on the trees for protection. It can eat right through it. It can eat through bark and stuff like that. And so you have these acid rain. The big problem is it will kill trees, plants, etc. And again, we just kind of looked at it. When stuff dies, again, it's going to produce a lot of organic waste, a lot of carbon products from that. Eventually, you get fossil fuels from this. Again, this is part of the carbon cycle here. Again, starts off with carbon dioxide in the atmosphere. Again, photosynthesis, we've been through that. Respiration, returns to carbon dioxide, etc. You get a lot of it from automobiles and factory emissions. So this is why they always try to say they try to improve the fuel economy of cars. It's a big thing now with electric cars, hybrid cars, etc. And again, this is why they were trying to limit the amount of fossil fuels that they were using, because they burn off a lot of carbon dioxide gas. And there's other pollutants too, but carbon dioxide gas is that greenhouse gas. Yeah, we talked about it. Again, you probably heard this a lot in the news and stuff. They talk about the carbon cycle, burn of fossil fuels, tree clearing, so you don't have as much, right? So you clear trees, you don't able to absorb as much carbon dioxide from the atmosphere. And then we've talked about acidification, greenhouse gas. And again, carbon dioxide gas is not the only greenhouse gas. A big one is methane. And again, you get that from manure and stuff like that. So this is a big thing when you have animal farming. That increases the amount of methane a lot, and that's a big greenhouse gas too. So it's not just carbon dioxide. Again, we need some greenhouse gases too. Otherwise, the planet will be too cold. So again, it's kind of a fine balance between it. Nitrogen cycle. So again, there's nitrogen in the atmosphere. So this is N2 gas. This one is much harder to use because this is not as reactive. Nitrogen gas is not very reactive. And again, we'll talk about this in class. So a lot of this stuff we'll talk about in class. So nitrogen gas is not as reactive as something like carbon cycle. And actually, only a few organisms use nitrogen because nitrogen is hard to break this nitrogen bond. So basically, nitrogen has what they call a triple bond. It's hard to get this to react. So very few organisms actually use nitrogen. There's only a few. There's a few. It's mostly just bacteria. They can break this down. And again, nitrogen is important for fertilizers. So we need these bacteria to break down this nitrogen gas in the atmosphere. And remember, most of the atmosphere is like 78% of it is nitrogen gas. And so bacteria will break down this nitrogen gas and then put those nutrients into the soil. So again, we need nitrogen for the soil. Whenever we buy fertilizer, they'll tell you how much nitrogen and phosphorus is in there. So again, those are important fertilizers in there. If it's too much, if you have too much fertilizer and stuff, a lot of this stuff can round off into waters, can cause these waters to have too much plant life and algae, and that can kill fish, play with the ecosystem also. So again, we have this kind of a fine balance among everything. And again, we kind of talked about this. So the nitrogen comes from the ground, from the air. Bacteria and stuff can form in terms of ammonia. So again, ammonia is used to make fertilizers and stuff like that. Again, this right here is what they call a nitrite. And then this is a nitrate. So again, when you buy fertilizers, you usually buy them in this form, like ammonium nitrate, ammonium nitrite. And we'll look at this in class a little bit. So again, this puts nutrients into the soil. So again, just like a carbon cycle, there's a nitrogen cycle. The only difference is nitrogen fixation is to put ammonia into the soil. And again, ammonia is NH3. Is that only bacteria can do it. So it's not like plants can't do that. Only the bacteria in these plants and stuff can fix this nitrogen fixation. And again, just basically the same things. You can have form acid rain because what happens is you can form something called nitrogen dioxide, NO2, and you end up with something called nitric acid. Again, a lot of this is chemistry. We're not going to worry too much about it. Just realize that it can lead to acid rain. And then if you destroy forests, grasslands, wetlands, we've heard this enough in there, you can release a lot of that stored nitrogen because plants and trees are not using that into the atmosphere, and again leads to like I said, acid rain and pollution, etc. And again, let's just kind of go through again. A lot of these are just basically the same type of concepts. So you get nitrogen, you end up with nitrates eventually from these nitrogen fixing bacteria. Nitrates are fertilizers. If you have too much of it now, when it runs into lakes and oceans now, it can cause algae, growth of a growth in plant life that can actually suffocate lakes because it grows at the surface. And so a lot of fish can die because they don't have access to air and stuff like this. You all need a little bit of oxygen in the air for these fish to breathe. So you have some oxygen actually dissolved in the water. So if you have all this increased runoff and stuff, you can suffocate a lot of fish life, etc. Again, we have the phosphorus cycle. So again, basically, a lot of this stuff works basically the same way. Phosphorus really comes basically from the Earth's crust and from living organisms. Again, remember, if you look at DNA and stuff, there's a lot of phosphorus in there. For fertilizers, you need phosphorus. So again, phosphorus is important for growth life. In fact, if you ever go buy fertilizers, that tell you how much phosphorus is in there. So again, there's a finite amount that you need to maintain plant life. Again, if this stuff goes into streams, this over agriculture and stuff, again, it can go into streams, cause all these plants and stuff to grow in these lakes and oceans, and it can suffocate fish life, etc. Some phosphorus also comes from rocks too, though. So again, this is more like an abiotic relationship too. So it comes from rocks. A lot of that phosphorus comes from rocks and stuff. Well, I'll tell you exactly what I need, what I want you to know from some of these cycles with it. But then phosphorus will come off from soil, from rock erosion. So rock erosion will pick up a lot of phosphorus in there. Uh, you end up with, this is called phosphates. And again, that's important for fertilizers. Plants need phosphates in order to grow. And then you have all this kind of system um, with it. And again, plants are eaten by stuff like snails, animals. So again, that's how you get phosphorus into your body. One last thing, talk about Earth's rocks. So Earth's rocks are recycled very slowly. There's different types of rocks. There's igneous rocks, sedimentary rocks, metamorphic rocks. Metamorphic rocks are like more like lava. Sedimentary rocks are rocks that form deep underground. So underground, the deeper you dig, you have a lot of pressure and a lot of heat. This is actually why diamonds are formed underground. So to form diamonds, it's just carbon. You need to go deep underground the way they're formed naturally, and they're grown under a lot of pressure with that. And again, and then these things actually can transform into each other. So secondary rocks are the lowest ones. Heat and pressure, you can form metamorphic rocks. Again, this is more like lava with that. And again, eventually you can end up even igneous rocks with that. So again, there's a rock cycle associated with stuff also. Basically, in the very end, a couple of takeaways from this. Water, nutrients, and minerals are recycled through biogeochemical processes. We need these to support Earth, and we need these for sustainability. And again, it's just a complicated system. It's all kind of a symbiotic relationship with each other. For Zoom discussions, what I want you to do, and again, just a little bit of homework, is to find something in your home that is converting energy from one form to the other. And then what form did the energy start in and what form did the energy end up with? So again, just kind of be creative. Look at your house and say, okay, this is forming energy. What form to begin with? Look at how energy is formed from one process to the other. And again, thanks for listening and have a good week.